Second trend that we want to discuss is the atomic size trend. Okay, the size of the atom in the periodic table. So the size of the atom is difficult to be defined. It is hard for us to measure the size of the atom exactly because the atom is not like a ball that we can see the end line of the ball. Okay, if we have an atom, okay, it is hard to define its size, okay, because there is no clear end. There is no clear end of the atoms. Okay, because of the electron cloud is the one that determine the size. So the bigger the electron cloud, okay, then the greater the size, the bigger the size. Okay, because we have discussed the orbitals before. Orbital is the same as this. Okay, it has no clear end. It is depends on the movement of the electron itself actually. So if the electron move further, then the size will be bigger. Okay, but there's no clear end. Okay, if we put a marble guli dekat dalam balon kan, kalau kita letak guli dekat dalam balon, guli tu hanya boleh bergerak dekat dalam balon tu je kan. Okay, because we have the end. Kita ada penghujung balon. Dia tak sama dengan atom. Okay, dia tak ada hujung yang elektron tak boleh pergi keluar daripada garisan, tak ada. Okay, tak ada exact garisan akhir tu, tak ada. Okay, due to that, to solve this, to measure the size of the atom, okay, is by measuring the distance between the nucleus of the two atoms in a molecule. So if let's say we have this molecule, okay, we can measure the radius by measuring the distance from the first point, the first nucleus to the second nucleus. This is the diameter, right? Divide by 2, then we'll got the radius. So we know that the longer the radius, the bigger the size of the atom. Okay, but it's okay. We are not going to calculate, no calculation on the radius and the size here. Okay, but you just need to know the trend of the size of the atom. When it is going down the group, the size will increase because of the atomic radius that is increased. And then across the period, the size decrease. Okay, from the left to the right of the periodic table. When we are using the term across here, across the period, it is always from group 1 to group 18. It is never from right to the left. It is always from left to the right of the periodic table. Okay, so going down increases, going across the period decreases. Okay, so look at to this. It shows the trend. Okay, let's look at to the period 2 elements. Okay, lithium, beryllium, boron until neon. We observe that the size decreases across the period 2. Okay, period 4, potassium until krypton, the size decreases. Okay, that is why the trend across the period is the size or the atomic radius decrease as for the group 1 from hydrogen to cesium, we observe that the size increases, okay, because of the trend. Going down the group, the size increases. Okay. So you have to be able to explain why these two trends happen. Okay, why across the period decrease, going down the group increase. Okay, there are two factors that determine the changes in the size or the difference in the size of the elements. The first factor is the effective nuclear charge. Okay, that is felt by the valence electron. Okay, effective nuclear charge is actually the net charge felt. The net charge means the net attraction felt by the valence electron towards the nucleus. And then the second factor is the principal quantum numbers of the valence electron. Okay, which is n of the valence electron. Okay, these are two factors. Let's look at one by one. Okay, the effective nuclear charge is the factor that determines why across the period the size decreases. Okay, this is because, okay, let's look at to the Zeph explanation. Electron that is moving across the period do not experience the same nuclear attraction. Okay, if let's say we have a sodium. Okay, we have a nucleus of the sodium here. This is the first shell, second, and the third one. We know that the sodium has 11 electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we also know that at the nucleus we have 11 protons. So the nuclear charge, the charge at the nucleus is plus 11. Okay. However, all these 11 electrons around the nucleus of the sodium do not experience the same attraction force towards the nucleus. Okay, they do not felt the same strength towards the nucleus. Okay, this is because the inner electron will experience a stronger attraction as compared to the 8 electron in the second shell. And of course that the outermost one will experience the weakest attraction towards the nucleus. Okay. And then this is because the inner shell or the inner electron are said to shield or to screen the outer electron from the full charge of the nucleus. The inner electron are the one that made the outer electron do not experience the same force towards the nucleus. Okay, they are giving shielding effect, okay, or screening effect to the valence electron. Okay, they makes the valence electron or the outermost one experience or felt a weak attraction towards the nucleus. Okay, by the screening effect or shielding effect. How this shielding or screening effect arise is actually due to their electron-electron repulsion. We know that when we have all negative species around the nucleus, what they do is they will always repel each other. So the repulsion that is happen, okay, between the inner electrons will give a shielding effect. It will shield. Dia akan hadang apa tu, tolakan-tolakan yang berada dekat dalam ni, menyebabkan outer electron ni dia tak rasa attraction yang sama towards the nucleus. Dia repulsion yang berlaku tu shield. Dia macam jadi perisai. Okay, menyebabkan outer electron experience weak attraction towards the nucleus. And then the size of the atom is actually depends on how strong the attraction between the outermost and also the nucleus. It is because if the outermost experience a stronger attraction towards the nucleus, it will make the electron cloud shrink, okay, towards the nucleus. But if the valence electron experience a weak attraction, it will make the size of the electron cloud expand. Okay, kalau attraction dia lemah, dia punya electron cloud akan lagi besar. So that the size of the atom will be bigger. But if the outer electron experience strong attraction, so dia akan moving towards the nucleus, it will make the size of the atom shrink and it is smaller. So that is why we are looking at the effective nuclear charge that determine the size of the atom, not just the nuclear charge. Nuclear charge is the total proton that we have at the center. But effective nuclear charge are the net charge felt by the valence only towards the nucleus. Okay, so effective nuclear charge here is defined or it is explained as the net positive charge attracting the valence electron. And how can we determine this effective nuclear charge or ZEF? By using this formula. ZEF is equal to Z minus S. What is Z? Is the proton. What is S? Inner electrons. That is why we learn how to determine how many inner electrons first before we learn on this effective nuclear charge. So ZEF, if the ZEF is high, means that the attraction between the valence electron and the nucleus is strong. Okay, when the attraction between the valence electron and the nucleus strong, then the size will be small. But if the ZEF is low, means that the attraction between valence electron and the nucleus weak, so that the size will be greater. So the relationship between ZEF and the size is inversely proportional. Okay, so let's look at how different ZEF will make different size of the element that come from the same period. Okay, so look at to the element that come from period number 2. We want to compare between lithium, beryllium, boron, carbon, nitrogen. Lithium, Be, boron, carbon, nitrogen. Okay, so lithium has 3 electrons, 4, 5, 6, 7. Calculate the ZeV value. Before that, the configuration. Okay, electronic configuration of lithium will be 1s2, 2s1. Beryllium 1s2, 2s2. Boron 1s2, 2s2, 2p1. Carbon 1s2, 2s2, 2p2. Nitrogen 1s2, 2s2, 2p3. Okay, so calculate the ZeV value. ZeV is equal to proton minus inner electron. Okay, so ZeV for lithium will be how many proton for lithium? It has 3 proton. Okay, so 3 minus inner electron. How many inner electron? This inner electron. Okay, so 3 minus 2, so it is equal to plus 1. Okay, beryllium, identify inner electron. It has 2 inner electron. Boron, 2 inner electron, 2 inner electron, 2 inner electron. They have the same number of inner electron actually. Okay, but different proton number will make ZeV value become different. So ZeV for Be will be 4 minus 2 inner electron equal to plus 2. Boron will be 5 proton minus 2 inner electron equal to plus 3. For the carbon, it has 6 proton minus 2 inner electron equal to plus 4. Nitrogen will be 7 inner electron minus 2 equal to plus 5. So if we continue to the next element, oxygen, fluorine, neon, we'll observe that the ZeV keep on increase. Okay, as the trend that we have observed now. Okay, the ZeV value increase from plus 1 to plus 2, plus 2 to plus 3, plus 4, plus 5 across the period to show that the attraction between the valence electron, see the valence electron, this is the valence electron of lithium, this is the valence electron of beryllium, these are the valence electron of the boron, carbon, and the valence electron of the nitrogen. Okay, so when the ZeV increases means that the valence electron will experience a stronger attraction towards their nucleus. When they experience a stronger attraction, it will make the electron cloud shrink, pull towards the nucleus. That is why the size decreases going across a period. Okay, so this is the explanation. ZeV increases across the period. Okay, so when the ZeV increases, means that the attraction force between the valence electron and nucleus increase so that the size decrease across the period. Okay, so you have to have at least these 3 points, but please don't write it as ZeV only, write it as the effective nuclear charge. Okay, so these are the first factor, which is the effective nuclear charge factor. The second factor that determines the size, okay, or the trend of the atomic size going down a group is the value of the principal quantum numbers of the valence electron. Okay, so going down within a group, the principal quantum numbers of the valence shell will increase. Okay, for example, when we have a lithium, sodium, and potassium here, okay, lithium is come from period 2. Okay, so when it comes from period 2, so if we write the full configuration, it will be 1s2, 2s1. For sodium, it is 11, so 1s2, 2s2, 2p6, 3s1. And for the potassium, it is 19, so configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. 4s1. Okay, so when we look at to the configurations of these three elements that come from the same group, okay, they last with the same trend, which is 2s(n)(s)(1). But the difference, okay, look at that is the similarity. The difference is at the n value. Okay, and for the principal and for the valence electron. Okay, these are their valence electron in 2s, in 3s, in 4s. So the valence electron, okay, the principal quantum numbers of the valence electron increases going down a group. That is why the size increases. Okay, or if we try to draw the atoms, if we have a lithium, it has only 2 shells. But this is the nucleus. But if we have a sodium, it has extra 1 shell. As for the potassium, since that it lasts with 4s, so it has until n equal to 4. Okay, if we label it, this is n1, this is n2, this is n3, this is n4. So of course that going down a group, when the value of the principal quantum numbers of the valence electron increases, it will make the size of the electron cloud bigger, so that when the size is bigger means that the valence electron of the elements, this valence electron, this valence electron, this valence electron experience a weaker attraction. So more further, lagi jauh elektron tu daripada nukleus, lagi besar size dia. Okay, the bigger the size means that the electron will be more further from the nucleus. Lagi jauh daripada nucleus. So more further the electron from the nucleus, the weaker the attraction between that electron and its nucleus. So the weaker attraction, the bigger the size. Okay, but why it has a weaker attraction and bigger size? Because of the value of the principal quantum numbers of the valence electron that is increasing going down a group. Okay, that's how you explain the trend in the atomic size. Okay, so these are the one from the slide. Okay, why going down the group the size increases? Because of the value of n that is increases. Okay, at the same time the ZEF value remain constant. Okay, the ZEF value for the element that come from the same group are the same. Okay, lithium, sodium, potassium, if we try to calculate their ZEF, lithium will be +1, sodium +1, potassium +1, because they come from the same group. Their ZEF value will be the same. So what is the factor that makes their size different? Is actually because of the n of the principal quantum numbers. So the larger the value of n, okay, the larger the size of the orbital. Okay, that is why the size, the atomic size increases going down a group. Look at to this trend. Lithium, sodium, potassium, rubidium, cesium. This is going down a group 1. See? From lithium to cesium going down a group, the size increases. And then lithium to fluorine. Okay, lithium to fluorine, this is actually going across the period 2. Okay, period 2, lithium, after lithium, beryllium, boron, and so on. Until fluorine, we observe that the size decreases. Period 3, sodium to chlorine decreases. Potassium to bromine decreases, and so on. It follows the same trend. And then fluorine, chlorine, bromine, iodine, if we connect this line, okay, we know that they come from the same group. So it follows the same trend, which is across the, going down the group, the size increases.